In lab, you guys were using springs and you discovered a thing called the spring constant, and also hopefully you understood work and elastic potential energy when it comes to the spring. Now, it is worth noting that um, work and energy are very, very closely related, and we're going to get more into that. That's sort of what this unit is about. We say that energy is the ability to do work, and also that work is the transfer of energy. So the two are basically the same thing. Work is energy being used, and energy is work being stored. So the two go together hand in hand. Now, if we get right into the lab, what you guys noticed was the amount of force required to stretch or compress a spring is directly proportional to the distance the spring is stretched. And you noticed that because you had to create a graph, and the graph had force on one side, and it had position or distance that the object stretched on the other. So we had force over here and distance down here. And you saw a line that started down in the bottom left and went up like this. Now that line denoted how much force it took to stretch the spring each distance that you pulled it. And it was a nice straight line. That tells us it's a direct proportionality. The slope of this line relates F and X. So F is equal to kx, and this did go right through the origin, so there was no y-intercept. K is the spring constant. It tells us how much force is required to stretch the spring a given distance. Now this graph is primarily of interest to us not because of the spring constant, but because of what we can do with it. Remember, work is equal to force times distance times the cosine of the angle between them. Well, in this case, we were always stretching the spring in the same direction that the force was acting. So the cosine is the cosine of 0, so that goes away. And that allows us to see that work is just force times distance. Well, that would be the area under this graph. And we did see that a little bit in our last section. So the area of this graph actually shows us how much work we've done to stretch the spring. And that's where this equation comes from. Remember, the area of a triangle is 1/2 the base times the height. Well, if we look at that, if we stretch the spring a distance x meters, then our height is given by the equation F equals kx. So this height is equal to kx. So the equation 1/2 base times height becomes 1/2 x times kx, which is just 1/2 kx squared. That's how much work it takes to stretch the spring. That's where this equation comes from. 1/2 kx squared is the work stored when we stretch a spring. So that's stored as elastic potential energy. So the work done to stretch the spring is identically the energy stored in the spring. So they're both 1/2 kx squared. They have the same unit. Both energy and work are measured in joules. And we can figure out how much work this spring can now do on something, because if we know how much work we've done to stretch it, that's how much work that spring can do on another object, because it's storing all that energy. Okay? So the gist of this lab was that work is the transfer of energy, and energy is the ability to do work. So when you do work on something, that energy is not gone. You've given it from yourself to whatever you did the work on. Okay? And it gives us another idea of positive versus negative work. When work is done on an object, the object gains that energy. When work is done, when positive work is done on an object, that object gains energy. When negative work is done on an object, the object loses energy. So positive and negative work can also be kind of a way of keeping track of which way energy is going. Is energy going into the object or out of the object? When we did work to stretch the spring, energy left us and went into the spring. When the spring would do work to pull something or push something, then energy would leave the spring and go into the object it's pulling or pushing.